Hi, let's talk about correlation. So in our last section, we talked about scatter plots, and we said that a scatter plot showed two numerical variables where you collect two pieces of information from each individual, and you show those as an ordered pair on a coordinate plane. All right, so vocabulary-wise, we call our variable the explanatory variable that's on the x-axis and the response variable that's on the y-axis, because the idea is that we're going to be manipulating or making changes to our explanatory variable and trying to use that variable to explain what we think is going on in our response variable. Okay, and so we're often asking this question, I wonder what will happen to my response variable if I make these changes. The response variable, the one on the y-axis, it measures the outcome. It's the measurement. It's the y-coordinate. It's the output, the dependent variable. And the explanatory variable is the one that we're making changes to. Okay, it's the one that's manipulated. So that is our x coordinate. It's our independent variable. It's the input to our equation. The other thing that we're trying to decide is there any sort of pattern? And we talked about saying things like, well, how strong is it? Is it positive? Is it negative? What does the slope look like? Is it linear? Okay, and being able to make predictions based off of that value. Okay, so one thing you might look for in an example, so for example, alcohol has many effects on the body. One effect is a drop in body temperature. To study this effect, researchers gave different amounts of alcohol to mice and measured their body temperature 15 minutes later. Okay, so if you notice what the researchers did, the researchers are manipulating the amount of alcohol, and then they are measuring body temperature. So basically they're asking the question, I wonder what happens to body temperature as we change the amount of alcohol that we give these mice. So our explanatory variable, the one that's being changed, manipulated by the researchers, that is the amount of alcohol, okay? And the response variable is the thing that's being measured. That is the body temperature. So in this case, we're always trying to decide, what are we trying to use to explain the change in this other thing? What are we manipulating versus what are we measuring? Okay, now when you go to talk about variables, it's extremely important that this is done in a way that you could imply that these are variable, that they are not constant, that they could be changes. You can always define your variable as a question, like capital letter who, what, when, where, why, how, question mark at the end, to help you be clear about the meaning. So on the scatterplot basic from our last lesson, we had this example where they went to several different countries and they measured the percentage of people who claim to have tried marijuana and the percentage of people who claim to have tried other drugs. Okay, so if I was going to talk about these variables, again, these are my individuals, my countries, okay? My variables would be the percentage who've tried marijuana and the percentage who've tried other drugs. Okay, if I go and I ask these two questions or I measure these two things, I can show differences in those values. I don't want to say my variable is marijuana or other drugs. That's not a variable. That's a category subtype, I guess. Okay, but that's not a variable. The variable has to be something that is very clear that the answer to that could be something different. Similarly, if you went and asked 1,000 people how many years of education they had completed after high school and whether or not they smoked cigarettes, your variables are going to be years of education after high school and do you smoke cigarettes, yes or no, not like education and smoking. Like, those are not variables. So when you state your variables, it's important that you imply that they could have a variable meaning to them. And if you don't do that properly, you will lose points for not having that as part of your answer. Okay. Now, again, when we are talking about relationships, we have this way to describe scatterplots. And I have this little acronym over here that helps me remember DUFS, D-U-F-S, the direction, anything unusual, the form, and the shape. Okay, so to make a scatter plot, or when you make a scatter plot, you always want to look at that. You want to describe what is the direction of it? Is it positive? Is it negative? Is there nothing going on there? So we have that direction, the kind of the idea of slope, and what are we predicting is going to happen. In general, positive means that larger values of X tend to be paired with larger values of Y. Negative means that larger values of X tend to be paired with lower values of Y. And no association means means that you can't make a prediction one way or the other. Form is generally we're referring to something being linear or non-linear. Does it look in general like if you drew a straight line through it that models the behavior, or does it look like a curve would better model the data? Strength is what we're going to be talking about today, and a scatter plot can show weak, moderate, or a strong association between those two variables. Basically, it's strong if your points don't deviate much from your form identified. So if you think it looks like a parabola and it really looks like a parabola, that's very strong. Or if you think it looks like a straight line, but it's kind of weak, scattered on there, then that would be a weak relationship. And again, we're going to be talking about that more today. Unusual features would be things like distinct clusters of points, things that don't match the pattern, things that we might want to be interested in, much like our outliers when we're talking about numerical data. So how strong is strong? So that's what today's lesson is. What do we mean by strong? Okay, so I look at my graph and I can kind of have an idea of a sort of judgment call thing, but I don't want to do that. I want to have a number, a mathematical number. So what we do is we have something called R. Okay, R is the correlation coefficient. And what this is this is a mathematical number that is calculated from your data that helps us classify how strong it is. It basically comes out to the average product of the z-scores for each ordered pair. You don't necessarily need to know how to calculate R, but you do need to know how to interpret R when you see it. Okay, so the way you might see R, so here I've got a couple of scatter plots with their R values calculated on here. So if something has no correlation, you're going to have an R value of 0. Okay, or something very close to 0. The closer it is to 0, the weaker that relationship. Something that tends to have a sloping down slope is going to be a negative R value. Okay, and that R value, the stronger the R is, the closer the absolute value is going to be to 1. If something is positive, you're going to have an R value that is also positive. And again, the stronger the relationship, the more line-like the points, the more those are going to have an absolute value close to 1. So a couple of features about R. First off, R has no units. R is a mathematical absolute value kind of number. Okay, it has no units, so R is not measured. It's not a percentage. It's not a feet or inches or anything like that. Also, if you interchange your X and Y, the R doesn't change. So if I put amount of alcohol on the x-axis and someone else puts body temperature on the x-axis, our two R values will be the same because of the way this is calculated. Linear transformations on X and Y don't change R. So all those things we talked about in the last chapter about means and standard deviations and how they change, like if you double all your data points, or if you subtract 5 from all your data points, if you do anything like that, that's a linear transformation. Multiplying by constants, adding or subtracting constants, it does not change the R value. So if you convert all your data points that were measured in Fahrenheit into Celsius by multiplying and adding, it's not going to change the R value. That R value will stay the same. R is always between -1 and 1. It's always between -1 and 1. Always. Okay, always between -1 and 1. And the closer that absolute value to R is to 1, the stronger your linear relationship is between two variables. So for example, 0.85 R is just as strong as -0.85. Okay, so the mathematical strength of that relationship, the quantity matters rather than the sign. Okay, the closer it is to having an absolute value of 1, the stronger it is. The closer it is to 0, the weaker it is. Okay, you only get a 1 or a -1 when you have a perfect linear relationship. So if you have something that's like 0.99999, that means it's just not quite a perfect line. It doesn't quite perfectly fall on a y equals mx plus b sort of line. The positive or negativity of R helps you determine direction. So if you know that your scatter plot tends to look like it has a positive slope, your R value will be positive as well. Okay, so when we are classifying R, it is generally, these are sort of general rules here. If your R value is in between -0.8 and 1 on either side of the scale, we would say that that's fairly strong. Okay, so anything in that 0.8 or above, positive or negative, those are strong. Anything between 0.5 and 0.8, we would call that a moderate relationship. And anything between 0 and 0.5 in either direction, that is a weak correlation between the two values. If you have r equals 0, that means there is no linear relationship, But just because you have a value of r close to 0 doesn't mean there's no relationship. In fact, there are certain cases where you might have a very strong curved parabola sort of relationship between the values, and you get an r value that's very close to 0. Okay, so you always want to interpret R across from its scatter plot. Here are 4, these are called Anscombe's quartet. These are actually 4 different data sets, and if you look at this, they all look very different. We have a sort of a moderate, a strong but linear here. This is very strong linear down in the bottom left corner C, but it does have an outlier. Got this weirdo vertical thing happening here with an outlier over here, and the other one is very curved. The interesting thing about this is that all of these have the same R value, and they also have the same least squares regression line, which we're going to talk about in the next section. Okay, so even though they all are very different data sets, they all have very different R values. There's another R value that's called the Datasaurus dozen, and I linked to this in case you would like to look at this again. But here it is, and these are another set of data points which you can watch, and they all have the same X and Y excuse me, averages. The standard deviation of the x coordinates, the standard deviation of the y coordinates, those stay the same. And they have a correlation, so that's your R, of negative 0.6. Okay, negative 0.06, sorry. So they have the same R value, all 12 of these different graphs, but you can tell that they're just very, very different. Okay, and I love that one of them's a dinosaur. That just makes me very happy. Okay, all right, so when we're talking about R, the thing to remember is that R is a mathematical computation of the strength of the linear relationship between X and Y. It is literally computed mathematically. It does not take a look back at the scatter plot and go, ooh, I said this was a strong linear relationship, but that looks really curved. So you, as the statistician, always have to go back and look at your scatter plot. The whole purpose for what we're doing in this chapter is to try to use relationships to make predictions. So even if you have a very strong, mathematically strong linear relationship, if you are seeing something that is a curve, like this B of the Anscombe's quartet right here, then that means that even if R is a very strong value, that a linear model is not the best fit, and we'd be better off to try to find a different model for our predictions. Okay. All right. So one of the things you need to be able to do is kind of predict an R value here. So I have several different graphs and several different R's, from positives to negatives, etc. So let's see if we can identify these pieces. Okay. So the first thing I'm going to do is I'm going to go through and just try to decide what I think is happening positive and negative. This looks positive, that looks negative, that looks negative, that looks like really very positive there. Negative, positive, and then I'm not real sure what to do with this guy right here. That doesn't look like positive or negative. If I'm out here, I can't really predict one or the other. All right, so that first one there, that's going to be R equals 0. That is no relationship. Okay. All right, this one down here, that's perfectly falling on that line. I want to look for something that's as perfect as it can be. So the strongest R can be would be 1. That would be G. Okay. All right, I have an R for F here. R equals negative 0.99. That means it's almost perfect, and it's negative. Okay, so I'm looking for something that slopes down and is a very strong relationship. That is probably this one right here. Okay, again, E is 0.9. I'm looking for something that's very strong, okay, but positive. Okay, very strong. So I have 2 that are left that are positive, and it looks like the one in the bottom corner here, that's going to be that one. All right. What I have left, I only have 1 positive left, so that's got to be C right there, 0.52. Okay. Then I have 2 negatives. One is negative 0.3, one is negative 0.7. Negative 0.3 is going to be weak, and negative 0.7 would be moderate. So the one that looks the most like the line is this guy up here, and the one in the bottom right corner that has much more scatter to it. So that's going to be our weaker relationship. Okay. All right. So to calculate R, using the formula that's on your formula sheet. The formula looks really gross. If you look over here, it says 1 over n minus 1, and that's because it's an average, but it's from a sample, so we're doing that n minus 1 thing as an adjustment. And you notice it says xi minus x bar over sx. That's basically the z-score for x. Okay, I want to find the z-score for every x coordinate, and then y minus y bar over sy, that's the y coordinate minus the average y over the standard deviation of y. That's basically the z-score for every y. So notice what it's asking us to do is to multiply those two together, okay, and then find the average distance right there. Now, in order to do this, if you were going to do this by hand, and I don't think you'll ever have to do this by hand, but I'm going to show it to you once. Okay, we're going to use our TI-Nspire to find some of these mean and standard deviation numbers for us. Okay, so I'm going to go to my TI-Nspire here, and I would encourage you to do this as well. So if you want to pause the video here and open up your calculator, you're going to do a list and spreadsheet, new document, list and spreadsheet, that's number 4. You're going to enter in the x coordinates, you're going to enter in the y coordinates. Okay, so if you want to pause the video and do that. Now, after I have this, I'm going to press Menu and Statistics, and then Stat Calculations. Oops, and I pressed the wrong one. Let me try again. Menu, Statistics, Stat Calculations. And the one that I want is number 2, which is 2 variable statistics, because I have 2 variables. Okay, it's going to ask me, what's my X list? Now I have a lot of things in here right now, so I'm going to say X, and my Y list is Y because of the way that I named those. So I named my X, I have to have a label up there. I labeled my X, X, and my Y, Y, and I'm going to drop those in. Okay, just like before, we're going to ignore the frequency list, category list, etc. I'm going to click OK. Okay, you can see I get some interesting numbers over here. Okay, so just like with one variable statistics, I'm getting basically this same thing twice. So notice I see X bar, that's 1.9. Okay, and then I've got an S, which is 1.08. Okay, so I'm going to go back and I'm going to write those in really quickly. Okay, here we go. Okay, so this is 1.9 and this is 1.08. Okay, and then I'm going to go back and I'm going to look for Y as well. Okay, so I'm going to scroll down. Okay, Y bar, the average Y is 79.8 and the S is like 12.26. 12.26. Okay, so there's my X and Y. And if I scroll down a little farther, notice I actually can get the R value, 0.967. So I'm actually going to write that down as well. Okay, so I'm going to go back to my paper here. So Y bar is 79.8 and 12.26. All right. So here we go. So what is happening then? And then, oh, sorry. And then R from my data value was 0.967. So this computes R for me. So by the time I get all of this business, I might as well have done this other value. Okay, so I'm going to delete this little square. I've actually done these computations already. So what I would do is I would take 5, okay, I'm trying to find the z-score, right, minus the mean of 1.8 and divide by 1.08. That gives me this z-score of negative 0.37. Okay, and then I would do the same thing with the y coordinate, 76 minus 79.8 divided by 2.26, and that gives me that z-score. I multiply those together, x minus x bar over s times y minus y bar over s, and I get this value right here. That's my for the single value. And the next thing I would do is I would do this for every single one of those. I would find the z-score for every x, the z-score for every y, and I'd find the product for each ordered pair. The sum of these comes up to 3.8306 when I do this. So what R is saying, it's basically like the average product of the z-scores. Okay, with an adjustment for a sample here. Since I have 5 ordered pairs, my sample size is 5. I would have 1 over 5 minus 1 times that 3.8306. And if you do this in your calculator, it comes up to 0.96. And sorry that my R is messy there. R. Okay, so it's about 0.96, which is what we pull out of the calculator as well. Okay, now you don't need to be able to calculate this by hand, but you need to have an idea of this is why, this is where this R is coming from. This is a mathematical computation based off of z-scores. Mathematical computation based off of z-scores. Okay, so when we're talking about R, okay, I need to be able to compute it, probably not by hand, but by pulling it out of my calculator, and I need to be able to interpret it. This 0.96, I think, okay, that's bigger than 0.8, so that's a strong, positive, linear relationship between X and Y. All right, so you need some calculator practice. I have 2 problems here, and I already have the answers so that you can check them. So what I would like for you to do is I would like you to try to come up with this R value from your calculator, and then write the interpretation, and then check your answers with what I have here on the screen. So this would be a time for you to pause, okay, and open up your calculator. Okay, and I'm just going to run through this first one with you. I've already got up a screen here, and I've got height and weight, so I've entered those in as an X and a Y. I've got names up here so I can grab them. Menu, statistics, stat calculations, 2 variable statistics. My X list was, and now I can't remember which one was height and weight. X was height, and my weight was Y. I'm going to click OK, and I'm going to scroll until I find R, 0.961, 0.961. Okay, I'm going to do the same with expenditures and graduation rates. So I've typed these in for the X, and I've typed these in for the Y. And I go menu, statistics, stat calculations, 2 variable statistics. I'm going to pick expenditures for my X, graduation rate for my Y. I click OK, and I'm going to scroll until I find R. There it is, 0.303, 0.303. Okay. All right, so R of 0.961, to interpret that, I would say there is a strong, positive, linear correlation between height and weight. And here, 0.303, there is a weak, positive, linear correlation or linear relationship, if you prefer that, between expenditures per semester and graduation rates. Okay. All right, so you need to make sure you put those in your calculator. You can actually get that R value out of your calculator. Practice with that. Okay. Now, there is one thing you have to be really careful about. Precise language really matters. Okay, R can only be calculated for 2 numerical values. So if you're talking about favorite color and the number of cups of coffee you drank in a day, you can't do that because we're talking about numerical variables. We're trying to show correlation. A lot of times we use that word association when we were talking about categorical data. Okay, and you can use that word association for numerical data as well. But when you're talking about categorical data, you're not talking about correlation anymore. Correlation is a word that we try to reserve for numerical data. Correlation means R. If you're asked to describe the correlation, it's asking you to compute and interpret the R value. All right, also remember that correlation does not equal causation. 2 variables that have a very strong positive correlation only means that large values of X tend to be associated with large values of Y. It doesn't mean that one is causing the other one to change. A lot of times 2 variables are associated because something else is going on. For example, and this is true, consumption of hot chocolate is negatively correlated with crime rates. Okay, so that means that high values of hot chocolate consumption tend to be paired with lower crime rates. Okay, now this doesn't mean that drinking a cup of hot chocolate makes you think, oh, well, I shouldn't go break into that bank now. No, both of these have this lurking variable behind them of cold weather. When the weather is cold, hot chocolate consumption tends to be high. Also, crime rates tend to fall when the weather is cold. Okay, so just because you see 2 things moving, even if it's very predictable, does not mean that one is causing the other. There might actually be a causal relationship with a variable you can't see at all. Okay, and later on we'll talk about how we can sort of prove causation. But for right now, we're just going to say there appears to be a relationship, there appears to be a correlation, but we're not talking about causation.